Science, second term, primary 6, unit 1, talking about force and motion. Today, in lesson 2, law of levers. Okay. I told you in the previous session that any lever is a rigid bar that rotates around a fixed point. The fixed point is called fulcrum. And any rigid bar is affected by two forces, which are effort force and resistance force. But the effort force is sometimes smaller than or larger than or equal to the resistance according to the type of lever. Okay. I told you also in the previous session, one of the importance of lever is increasing force. And the levers increase force by saving effort. Okay, I told you just few examples of levers that do this importance. So, if I ask you, do you think all types of levers increase force, or all types of levers save effort? Okay, in this lesson we are going to explain this point, but for sure, not all types of levers increase force or save effort. Okay. In this lesson, we have a mathematical equation that explains the relation between effort force and resistance force. This relation is between, again, effort force that exerted by person or made by person and resistance force that results from the weight of the body that I want to move. And this equation is called law of levers. Okay. Here we have an activity to deduce the law of levers. Let's start it.
Dear student, after determining the meaning of levers and their types, let's deduce the law of levers by doing the following activity. You need several heavy objects with different weight, a metal bar or long piece of wood, a strong rope, spring balance, and finally, metric ruler. What should you do? Assign the weight of the first object and let it be your school bag by using the spring balance. Therefore, you have determined the value of resistance. Hang the metal bar from the middle by the thread, the fixed point, where it is completely stable in an upright position. Fix the bags at one end of the metal bar. Fix the spring balance at the other end of the metal bar. Pull the spring balance down to produce the balance. Assign the balance reading at the balance. Therefore, you have determined the value of force. Measure the distance between the force and the fulcrum, which is known as the arm of force. Measure the distance between the resistance and the fulcrum, known as the arm of resistance. Repeat the previous steps while changing the weight of the object and its position, and also the position of the spring balance. Then, record the results in a table of your design. What do you observe? What do you conclude? If we assume that you got the following results from the previous activity.
Observation and conclusion from the previous video. Number 1, effort force arm. When I told you arm, I mean the distance. So, effort arm or effort force arm, it is the distance between the effort force and fulcrum. Again, effort arm, it is the distance between the effort force and fulcrum. Okay, number 2, resistance force arm or resistance arm. It is the distance between resistance force and fulcrum. So, if I ask you write the scientific term, it is the distance between the resistance force and fulcrum. Distance means arm, so the answer will be resistance force arm. Okay, here we have the law of levers. The law of levers states that the effort force that exerted by person multiplied by effort force arm must be equal to the resistance force that exerted or resulted from the weight of the body that I want to move multiplied by the resistance force arm. Here we have the distance between effort force and fulcrum is called effort arm, while the distance between the weight of the body that I want to move or the resistance force and fulcrum here in the picture is resistance force arm. Okay, there is an inverse relation between the force and its arm. What does it mean? Inverse relation means when the effort force is bigger, its arm must be smaller. So, again, inverse relation means when the effort force that exerted by person is big, so effort force arm must be small. And here in resistance force arm, when the distance between resistance force and the fulcrum became longer, so the resistance force that exerted by the body that I want to move will be small. Can you understand now the meaning of the word inverse relation between the force and its arm? When effort force is bigger, its arm must be smaller. Or when resistance force arm is smaller or shorter, the resistance force must be bigger. Okay. Number 1. After we explained the law of levers, which states that effort force multiplied by its arm must be equals to resistance force multiplied by its arm. Okay, let's look at the picture. Here we have the resistance arm equals to effort arm, right or wrong? Look at the picture. Okay, so from law of levers we can conclude that when resistance arm is equals to effort force arm, so for sure effort force will be equals to the resistance force. Again, if resistance arm, like in the picture, is equals to effort force arm, so the effort force will be equals to resistance force, and this is according to law of levers. Okay, the second case. When effort arm is longer than the resistance arm. Look at the picture. The fulcrum is on the right side. Can you see it? Okay. Look at the effort force arm. Yes, the effort force arm is longer than the resistance force arm, right? Okay. I told you there is an inverse relation between force and its arm. So here, effort arm is longer. So we can conclude that effort force is smaller, right? Okay, so when I told you effort arm is longer than the resistance arm, so the effort force is smaller than the resistance force. Why? This is according to law of levers. Okay, and I told you before, when effort arm is longer, for sure, the effort force is smaller, because there is an inverse relation between any force and its arm. Case number 3. When the effort arm is shorter than the resistance arm. Look at the picture. We can see or conclude that resistance arm is longer than the effort force arm. Okay, here in this case, effort arm is shorter or smaller. So according to the inverse relation between the force and its arm, the effort force here is shorter. So for sure, the effort force that exerted by person will be larger than the resistance force. Again, when effort arm is shorter than the resistance arm, the effort force is larger than the resistance force. Okay, did you know the effort force or resistance force, any force around us, are measured by Newton? So the measuring unit of effort force or resistance force is Newton. Okay, what about its arm or their arms? Effort force arm and resistance force arm. I told you the meaning of the word arm here is the distance, right? And we can measure the distance by what? Who can answer? Yes, any distance by meter or centimeter. So effort force arm and resistance force arm is measured by meter or centimeter. Let's start this problem. First we have to read the problem well. Okay, a force that has a value equals to 15 Newton. Okay, had an effect on a lever of the second class with a force arm equal 20 centimeter. Okay, if I told you, before I complete the question, if I told you force instead of effort force, This means also effort force. So we have here the value of effort force equal 50 Newton and the effort force or the force arm equal 20 Newton. Okay, here we need to calculate the resistance where the resistance arm equal 5 centimeter. Okay, before anything we have to write down the law of levers, which states that effort force multiplied by its arm equals to resistance force multiplied by its arm. And here in this problem we have effort force or the force equal 50 Newton, and we are going to multiply it with 20 centimeter like that, and this side must be equals to resistance multiplied by 5, which is the resistance force arm. So we are going to make division, and we are going to put the complete side, which is 50 multiplied by 20, in the upper side, while in the lower one we are going to put the number which is alone, like that. The resistance equal 50 multiplied by 20 divided by 5, and the answer will be equals 200 Newton. Another problem. Calculate the arm of force. Now he wants the effort force arm. In a second class lever, if the force equal 20 Newton, the effort force here equals 20 Newton. The arm of resistance equal 10 centimeter, and the resistance equals 80 Newton. Okay, before anything I told you before that you have to write down the law of lever, which states that effort force times its arm equals to resistance force times its arm. Here we have the effort force equals to 20 Newton, and we are going to multiply the effort force by its arm, which we wanted here, equals to 80, which is the resistance force, and multiplied by its arm, which is equal 10 centimeter. And we are going to make division and put in the upper side the complete one, which is 80 multiplied by 10 divided by the number which is alone, which is 20, and the answer will be equals 40 centimeter. I'm going to explain a very important point in this lesson: law of levers and conservation of effort. By applying the law of levers on the three types of levers, we find that in the first class levers we have three possibilities. Okay, explaining them. When I ask you what's meant by first class lever, it is levers which have fulcrum lies between effort force and resistance force. So the first possibility here in first class levers, arm of the force is equal to the arm of the resistance. Like here in the picture, look at the arm of force or the effort force arm and the resistance force arm, they are equal. So the first possibility, when arm of the force is equal to the arm of resistance, the force or the effort force is equal to the resistance force. Okay, do you think when the effort exerted by a person is equal to the resistance force or the weight of the body that I want to move. When the two forces are equal, do you think your body now conserve effort? What is the meaning of the word conserve effort? Conserve effort means save effort. Do you think now you are saving your effort? For sure, no. The amount or the force that you made equals to the force that exerted or resulted by the weight of the body that I want to move. So now I'm not conserving my effort or saving my effort. The meaning of the word conserve effort also has no mechanical benefit. So when the lever conserve or save effort, this means has mechanical benefit. But if the lever never conserve effort or never save your effort, this means has no mechanical benefit. Okay, the second possibility. Look at here the effort force arm. Yeah, the effort force arm here, or the distance from the effort force to the fulcrum, is longer than the resistance force arm, right? Okay, I told you there is an adverse relation between force and its arm. So when the effort force is longer, when the effort force arm is longer, so the effort force exerted by the person will be smaller. So when the arm of the force is longer than the arm of the resistance, like here in the picture, so the effort force is smaller than the resistance force. When your body do a very small force, this means you are conserving effort or not. Again, the meaning of conserve effort, save effort. Do you think now you are saving your effort? Yes, for sure. Conserve effort. Okay, so the second possibility here, conserve effort or save effort. And I told you when the type of lever or this lever conserve effort, so it will has what? Yes, a mechanical benefit. The third possibility here in the first class lever, look at here the effort force arm. Yeah, the effort force arm is smaller than the resistance force arm. Okay. Again, the distance between the effort force and fulcrum is smaller than the distance between the fulcrum and the resistance force. So, when the arm of the force is smaller, for sure the effort force will be larger. Okay, when the arm of the force is smaller than the arm of the resistance, so the effort force is larger than the resistance force. So when the person do a very large effort force, this means you are conserving effort? For sure no. Now, this lever doesn't conserve effort or don't save your effort, and this means has no mechanical benefit. So first class lever sometimes save effort. What about the second class lever? What's meant by second class lever? Who can remember? Yes, second-class levers, they are levers, a type of levers, in which resistance force lies between fulcrum and effort force. If you want to determine the effort force arm and the resistance force arm here in the picture, you can see that the distance from fulcrum to effort force, which is the longest distance here, is the effort force arm, while the distance between fulcrum and resistance force is the resistance force arm, which is smaller. Okay, so here in second-class lever, the effort force arm is always longer than the resistance force arm. So the effort force for sure is always smaller than the resistance force. Okay, we can conclude from that if your body makes a small force, which is the effort force is smaller, so you are conserving effort or saving effort. Okay, so all second-class levers conserve effort, and this means they have mechanical benefit. So, second-class lever always saves effort or has a mechanical benefit. A very important question. Give reason for the soda water, opener, and stapler save effort, or the nutcracker and wheelbarrow has a mechanical benefit. Both questions have the same answer, which is because they are second-class levers, where the effort force arm is always longer than the resistance force arm, so effort force is smaller than the resistance force. You got it? Okay. Let's start talking about third-class levers. Okay, who can remind me by the meaning of a third-class lever? Okay, a type of levers in which effort force between resistance force and fulcrum, like here in the picture. And if we want to determine the effort arm and resistance arm, okay, the effort force arm is the distance between fulcrum and effort force, which is a very small distance, while the resistance force arm is the distance between fulcrum and resistance force, which is the longest. So in third-class levers, the effort arm is always shorter than the resistance force arm, and so effort force is always larger than the resistance force. When your effort force is larger, so now you are saving effort? Okay, for sure, no. All third-class levers never save or conserve effort and has no mechanical benefit. So, third-class levers always don't save effort or has a mechanical benefit. Let's start this comparison between the three classes of levers. First-class levers. The location of fulcrum, effort force, and resistance force. Here in first-class levers, fulcrum is between effort and resistance force, while in second-class levers, resistance force is between fulcrum and effort force. Okay, third-class levers the effort force is between resistance force and fulcrum. Okay, the second point of comparison, force arm and resistance arm. First class levers have three possibilities. Force arm may be longer, shorter, or equals to resistance arm, while in second class levers, force arm is always longer than the resistance arm. But in third class levers, force arm is always shorter than the resistance arm. Okay, what about saving effort in the three classes? First class lever sometimes save effort. Second class levers always save effort. Third class levers always don't save effort. Let's start this exercise about the previous part. Complete. Number 1, the broom is a lever of the third order in which the space is longer than space. Okay, the broom is a lever of the third order in which the resistance force arm is longer than effort force arm. Number 2, levers of second type save effort because effort arm is always space than resistance arm. The answer: levers of second type save effort because effort arm is always longer than resistance arm. Number 3, the levers of first type save effort when the space is longer than the space. The answer: the levers of first type save effort when the effort force arm is longer than resistance force arm. Question number 2, what happened when? Number 1, the effort force arm and resistance force arm are equal. The answer: this type of lever don't save effort or don't conserve effort and has no mechanical benefit. Okay, question number 3, write the scientific term. Number 1, force times its arm equal resistance times its arm. The answer: law of levers. Number 2, a type of levers that always conserve effort. The answer: second class levers. Number 3, the type of levers where the effort force is always longer than the resistance force. The answer: third class levers. Question number 4, give reason for the second class levers always conserve effort. The answer: because effort force arm is longer than resistance force arm, so effort force is smaller than resistance force. Thank you for listening, my students. Hope you enjoy it, and good luck.